So here's a neuron. This is a multipolar neuron. So we see the cell body here, the nucleus. These are the dendrites sticking off that cell body. Here is the axon. Here would be the terminal end of the axon or the synaptic end bulb. These are the vesicles, and this is whatever cell this neuron is stimulating. All right. Now remember, we often refer to this as a synapse. And we can refer to this neuron as the presynaptic neuron because it's before the synapse. And this would be the postsynaptic, either neuron or cell. It could be a muscle cell, a gland, or it could be another neuron. So this neuron is transmitting a signal from this end where it receives the stimulus until this end where it releases the neurotransmitter. So how does this occur? Well, first of all, notice that we've got the ion gradients all set up here. So because of that sodium-potassium pump, we have high sodium outside, or in the extracellular side, and notice we have high potassium on the inside, and we have this voltage difference. We have more negative ions on the inside, more positive ions on the outside. Okay? When this situation is set up, we call this neuron resting. All right? It's a resting neuron. It's not being stimulated yet. Okay? It hasn't been excited, and it's just resting. Okay? Now, we can actually measure this electrical difference. Okay? And there's these little electrodes that you can stick the electrode in there and it'll measure this voltage. Okay? And when neurons are at rest, they have a certain voltage. And that's called the resting membrane potential. Okay? And typically neurons are at rest when their resting membrane potential is about negative 70 millivolts. Okay? Now, we have another name for this. We often refer to this cell as being polarized. Okay, and that's going to be really important because we're going to use some terminology here. And you don't understand this terminology unless you understand why we call this resting neuron polarized. Now, we use that word a few times, right? You might think of, the north and south poles of the earth. So one's on the north and one's in the south. So they're completely opposite. All right, that's why they're called poles. Sometimes we use polarized explaining when two people don't agree about something, right? So, I always like to use politics as an example. So, Democrats and Republicans are often polarized, all right? They're quite a bit different in some of their beliefs. So the reason why we called this cell polarized is it's very different on the inside versus the outside, okay? It's negative on the inside, it's positive on the outside, okay? So this cell is said to be polarized. Okay, so now that sets the stage. What could happen? Well, we see here this is where a stimulus is occurring. This could be a mechanical stimulus. So maybe this neuron is a pressure sensor in your skin, or maybe it's a stretch sensor in the urinary bladder. And when there's a mechanical stimulus, it stimulates at the dendrites. Or it could be a chemical stimulus. So maybe it's a chemical, maybe it's another neurotransmitter that might be stimulating this cell. Either way, it has to have a receptor for that stimulus, either a mechanically gated ion channel or a ligand-gated ion channel. So those would be at the dendrites. So let's say the stimulus occurs. Whatever that stimulus is, it's going to open up channels, okay, ion channels. In this case, I'm showing that it opens up a sodium channel, all right? So let's say it's a chemical. The chemical attaches to the channel, it opens up, and it lets sodium in. Well, the first question is why? Why does sodium go in? All right, why doesn't sodium go out, or why isn't it potassium? Well, it's very specific to what the type of channel. All right, it's a sodium channel. But the reason sodium goes in is because we have that gradient. All right, this is called diffusion. When you have a lot of something on one side, and you let it go, it's going to go from high concentration, which was outside, to inside. Okay? All right, and then it might get stimulated here. So it might be getting stimulated all around these dendrites, opening up these sodium channels. And now we get this sodium entering the cell because of that ion gradient that we established using the sodium-potassium pump. Okay, so now we're going to look over at this graph. Okay, and this is the graph we always use to explain what an action potential is. So when the neuron is at rest, it's right here, okay? And we're sitting there at -70. It's not doing anything. Nothing's happening. Nothing happens. All of a sudden, this arrow is when you get a stimulus. And again, if you have a stimulus that lets sodium in, sodium is positively charged. So this -70 is going to go up, okay? It's going to go up because it might go from -70 to maybe -69, then -68, then -67, and so on and so forth, all right? Now, that process, whenever you go from negative up, is called depolarization. So why does that make sense? Well, if you're polarized at -70, but now you're bringing in positive, you're becoming less different, right? You're becoming less polarized. So we call that depolarization. Now, nothing's going to happen. This neuron is not going to do anything unless the voltage hits a magic number. And the magic number we call threshold. Threshold for this purpose is -55. So that means is sodium will keep coming in. Nothing's going to happen to that neuron unless it gets to -55. If it hits -55, that is the voltage, okay, that opens what we call voltage-gated sodium channels. Those channels occur right here at the trigger zone, all right? So the only way to get those channels open is if you go from -70 to -55, okay? So those are voltage gated, right? Because we went from a voltage of -70 to -55, and that opened the channels. Notice what sodium does there. It goes in. Why? Because we have that sodium gradient. We have a lot of it out here, so it's going to flood inside. Then what happens? Well, that's going to depolarize this area. All right, and then what's that going to do? Keep opening up more and more sodium channels. All right, and because you let a ton of sodium in, you get this huge spike in this curve. All right, you get this dramatic depolarization. So this little bit here was due to these channels. All right, and that's called a graded potential, just a little bit of change. This change here is due to the voltage gated channels. And every time you open sodium channels here, it'll trigger sodium channels next door. So you keep opening these sodium channels all the way down the axon. Now, when the voltage gets to +30, that's the voltage that opens up a different type of voltage gated channel. That opens the potassium voltage gated channels. And what direction is potassium going to go? It's going to go out of the neuron because you have a lot of it on the inside and little of it on the outside. So potassium is going to want to go out of the neuron. And that brings you back down to more negative. That process is called repolarization. And that happens behind the depolarization. So you kind of depolarize, and then behind it you repolarize. All right. Sometimes you go a little bit below the -70, and that's called hyperpolarizing because now you're getting even more negative than the -70. All right. So this is the action potential kind of wave that occurs all the way down the axon until it gets to the calcium channels. Remember those calcium channels? Those open when these last channels, these last sodium and potassium channels open. And then calcium goes in, and we know what happens because we learned about the neuromuscular junction. That releases the neurotransmitter, and then we stimulate whatever cell this is. Okay, and this cell would have to have ligand-gated channels here that open in response to the neurotransmitter. All right, so that's how a neuron sends an electrical signal down its axon. It uses mechanical or chemical gated channels on the dendrites. We either get to threshold or we don't, but if we do get to threshold, we're going to open the sodium channels and cause depolarization. And then after that, we cause repolarization. Now, the final thing is we have to have the sodium-potassium pump again. Because if we let this action potential travel down, all of a sudden we brought in a ton of sodium and brought out a bunch of potassium. So the only way for this neuron to send another signal is to send those ions back where they were in the beginning by using the sodium-potassium pump. All right, so that's how a neuron works. Again, this idea of threshold is really important because it's kind of like pulling the trigger on the neuron, and that the only way the neuron is going to fire is if you reach that threshold. So you might get small little changes. All right, so this is kind of a similar graph. There's the -70, but notice this little depolarization was a small stimulus that didn't reach that threshold. And then you had another one that didn't do it. Then you had another one that didn't do it. So these little depolarization events weren't enough to trigger an action potential. But then you have this one here, so the stimulus was enough. So a larger stimulus depolarizes above the threshold, and then that's what we're going to trigger the action potential with. So these are all little depolarizing events. Now these are actually hyperpolarizing events. So hyperpolarized is when you go below the -70. And those are often used to inhibit the neuron or prevent the neuron from sending an action potential. So all these little changes are called graded potentials. Only if you hit threshold will you trigger an action potential. So this is a little bit of a summary. This was from a different book. I kind of liked it. But you'll notice it kind of breaks down this action potential wave again. So there's the stimulus. There's the opening of the either mechanically gated or ligand gated channel to get you to threshold. The moment you get to threshold, notice the green phase here is when the sodium channels are open. Then you get to that +30, they close, and then this yellow phase is when you have opening of the potassium channels. And sometimes you get this hyperpolarizing event, and then we get back to resting membrane potential. So 3 important numbers to remember. -70 is rest. -55 is threshold. That's where you get opening of the sodium channels. And then +30 is where you get closing of the sodium channels and opening of the potassium channels. This is another kind of review. This is just showing us where all these channels are. All right, so if you think of a neuron, if these are the dendrites, that's where you're going to have the receptors, right? The ligand or mechanically gated channels. Cell body, that's going to just basically be housing the nucleus. Here's the axon, and these little axon terminals are where you have all those voltage gated channels, and then right at the ends is where you're going to have the calcium channels in order to stimulate exocytosis of the neurotransmitter. So again, kind of a review slide. This is also kind of a review slide comparing what we mean by a graded potential to what we mean by an action potential. So potential means the electrical activity changed, right? You got some sort of change in that electrical number, right? That -70. If it's graded, it occurs along the dendrites and cell body. It doesn't move, right? Action means it's propagating or moving down the axon. And these, again, graded doesn't necessarily mean you're going to trigger an action potential. So they can be variable, all right? They can be a little bit of change, a little bit more of a change. They can be hyperpolarizing. They can be depolarizing. But the only way they're going to trigger an action potential is if you reach threshold, all right? And then if you get an action potential, you're using those voltage-gated sodium and potassium channels. That's going to propagate the communication down the axon until you cause release of the neurotransmitter. Here's kind of a big picture. So this is where you kind of make the connection to maybe an everyday event. All right. So notice we have a person here, right? They got a brain in there. They're using a pencil. All right. So how do they know that pencil is actually in their fingers? They have a sensory neuron. All right. So this blue neuron is a sensory neuron. It's a touch sensor. Now notice right at the tip here, they show this little blue arrow. That means once you pick up that pencil, you might be getting minor little stimuli, a little bit of touch that forms little graded potentials, all right? The only way it's going to stimulate so you perceive that there's actually a pencil in between your fingers is if it reaches threshold. If you get enough pressure on your fingertips to reach threshold, it's going to produce an action potential. So now we see this black arrow representing the action potential. So that's all that sodium and potassium voltage-gated channels. It goes into, in this case, it goes into the spinal cord. Then we got to transmit it up to the brain. It's going to then trigger an action potential in this purple neuron, which is an interneuron, which sends it to this area of your brain, which we're going to learn another day about the thalamus. And then it triggers another cell to produce an action potential out here in the cerebral cortex. And that part of your brain is what interprets, all right? It interprets, oh, I have a pen in between my fingers, all right? So notice what that used. It used one sensory neuron. It used two interneurons, which are in the CNS, to get to the area of your brain that you can process the fact that you have a pen in between your fingers. So then what do you have to do? Well, you want to be able to move the pen. Well, how are you going to move a pen? Well, now you got to have a motor neuron coming out of the brain, down the spinal cord, all the way to your muscles, right? And there are the little neuromuscular junctions that are then going to stimulate muscle action potentials so you can contract muscles. So all of this happens every time you pick up a pen and then have to use that pen. You're producing a bunch of these little action potentials, transmitting quote-unquote information to the CNS and then away from the CNS. Okay, that's probably the end of that video. And then we're going to start a new one talking about why myelination speeds up the rate at which an action potential moves. And then we'll move on to some other topics.